Hello and welcome back to Automata, Grammars, and Computability. In this class, we will continue to talk about context-free grammars and start relating them to push-down automata. As before with finite automata and regular languages, where we show that they were equivalent, there's also an equivalence between context-free languages and push-down automata. The main theorem then is a language A is a context-free language if and only if some push-down automata recognizes A. And so this is a two-way implication. IFF means if and only if, and the implication goes both ways. Looking at the Chomsky hierarchy some more, we today are going to be looking at context-free languages and push-down automata. So we are living here in this circle, and then of course we're focusing on these parts in here. One thing you'll notice with the Chomsky hierarchy is that everything can be written as a language, right? So recursively enumerable language, context-sensitive language, what we're working on today, which is context-free languages, and then regular languages below. And each one of those, so these are the languages, each one of those has a sort of machine that recognizes it. So a recursively enumerable language has a Turing machine to recognize it. A context-sensitive language has linear bounded automata to recognize it. Context-free languages have push-down automata to recognize them. And as we've talked about before, regular languages have finite automata to recognize them. And so today, what we're going to be talking about is context-free languages and grammars, and then push-down automata. So we are living right here. Let's go ahead and talk about what a push-down automata looks like. I have here something that looks a lot like an NFA. This is what we would call finite control. A push-down automata has that same finite control, and it has the same sort of input that you've had before. I'm going to call that as a tape. And as we've seen before, the finite control is going to read in each element of that tape and have it go through the states accordingly. So we've seen all that before. The thing that is new is a stack. There is this ability to add the stack to the finite control and actually add or remove elements from it. In other words, a push-down automata operates like an NFA, except you can write, add, or read removes symbols from the top of a stack. And the phrasing for that, of course, is you can push elements to the top of the stack, or you can pop elements from the top of the stack. A stack is a sequential data structure that you can only access from one end. The way you visualize this is the elements you store are listed from bottom to top, and you can add something to the top, which is called a push operation, or you can retrieve and remove the topmost element, which is called pop. Let's talk about the stack a little bit more. In a push-down automata, that stack is going to start out empty. And as the push-down automata operates, it's either going to push or pop symbols on or off the stack. And there's also this thing where we're going to transition based on the top stack symbol and the input symbol. So remember that we still have this finite control, this thing that looks like an NFA. And what we're going to write on here is between two states, we can write a letter, which we've seen before. That's the letter that we transition on. And we're also going to write the stack symbols with an arrow. So what this means is that we transition based on this input symbol, which in this case is A, and then I have C and then an arrow pointing to D. That means we're going to pop C off the stack and push D onto the stack. I do want to point out that the stack does not have to be empty for the PDA to accept. One caveat that I have is that the pushdown automata can transition using the arrow that's shown only if the next input symbol is in fact the symbol that we've written and the top of the stack is the symbol that we've written there as well. So in this case, I'm saying I want to read the letter A from my input string, which it is, and if the top of the stack is C, then I can pop C and continue on. Otherwise, I would not be able to transition from one state to the other. I think we have enough information to go ahead and talk about the formal definition of a pushdown automata, which is going to be in tuples as usual. A pushdown automata is a 6-tuple: Q, sigma, gamma, little delta, Q0, and F. Q is a finite set of states. Sigma is a finite input alphabet. Gamma is a finite stack alphabet. Q0 is the initial or starting state, and F is a set of final or accepting states, which is a subset of Q. And delta is a transition function where delta goes from Q cross sigma with epsilon cross gamma with epsilon to the power set of Q cross gamma with epsilon. Let's just look at a couple of things here. The input alphabet and the stack alphabet don't necessarily have to be the same thing. So often they are the same alphabet, but they do not have to be. As before, we have Q0, which is a start state. We've seen that before. And we've seen a set of final or accepting states as well, which we normally write with the double circle. The transition function, we've seen that before as well, but now my domain and range look a little bit different than they did before. Let's just relate the formal definition, what the components are, to the picture. So first we have the states, which are drawn inside the finite control. So you'll have, as before, circles, and there will be, of course, arrows between those circles. Those circles are the states. Next, we have the alphabet, which is what comes from the input string. So this is sigma. And so this input string is some sequence of letters in sigma. The next thing we have is the stack alphabet, which is gamma. That's what gets pushed and popped onto this stack here. And next we have our transitions. So our transitions are written as a input string letter, so something in sigma followed by something from gamma to something in gamma. Finally, we have our initial and final states. So in the picture, we usually draw that arrow going into that initial state, and then our final state will have the double circle in it. Let's go ahead and talk about the parts of delta, the transition function, and break it down. The function is Q cross sigma epsilon cross gamma epsilon to power set of Q cross gamma epsilon. Q on the left-hand side indicate the pushdown automata's current state. Gamma sub epsilon on the left-hand side indicates that the pushdown automata has a potentially empty symbol on top of its stack. Sigma sub epsilon means that the pushdown automata is going to look at the current input symbol, but it may also have epsilon transitions, which we've seen before with NFAs. On the right-hand side, we have P, which means power set, which means that at each step in the computation, the pushdown automata may have several options. So Q on the right-hand side means that each option specifies a new state, so there's multiple states that you can go to. And then gamma sub epsilon means that you are going to push a new element to the stack, but potentially that could just be the empty element. All right, so we'll see this again a couple of times as we do some examples. The reason that the stack is helpful is because a DFA or NFA can only remember, quote unquote, a finite amount of information, but a pushdown automata can remember an infinite amount of certain types of memory information in one memory stack. And that's why the transition function looks a little bit different in that it has to hold not only the symbol that we're transitioning on, but also what you're going to push and pop to the stack. Let's look at an example for the pushdown automata for the language where there's an equal number of zeros and ones. So k zeros followed by k ones, for example. All right, if we want to build the pushdown automata, we should think about what the stack is going to look like. All right, so we want to make sure there's an equal number of zeros and ones, so all we have to do is keep reading zeros, and then we push those onto the stack until we read a 1. And in some sense, that stack allows us to count the ones. Then, to make sure that they're equal, we read the ones from the input, and each time we read a 1, we pop a 0 from the stack. We enter the accept state if the stack is empty. Consider again that we need to have this picture where we have both a finite control and a description of the how we're reading the elements and then the stack. All right, so even though I said all those 3 steps about reading zeros and pushing it onto the stack, we still need to formalize this. So let's look at that. After developing your intuition for what's being read and written and pushed and popped onto the pushdown automata, you can go ahead and start to think about how to write it in terms of the 6-tuple, which is how we formalize our description. The 6-tuple consists of Q, sigma, gamma, little delta, an initial state, which I'm calling Q1, and the final state, F. And I'm going to go ahead and tell you the answer for this particular language. We are going to start out with 4 states. So Q1 is my initial state here. And then I'm going to have 3 more states on top of that. My alphabet is just going to be 0 and 1. And my gammas are going to consist just of the 0 and then this dollar sign. So this is what we call this like phantom stack symbol. Which can be used to signify like the end of the stack. We have a transition function, which I'll get into in a moment. Q1 is going to be my initial state, and my accepting states are going to be Q1 and Q4. And here, Q1 actually makes sense because that would be the empty string. So if you have an empty string, then that is in fact an equal number of zeros and ones, so it should be accepting. And then somehow we're going to count and push and pop to get 0 to the k, 1 to the k for k greater than 0. So now let's look at the visual representation of a pushdown automata. So I'm going to go ahead and show you what the circles and arrows are going to look like. That will get you a sense of what it should be. All right, we'll start with Q1, and because I can accept the empty string, I know it's going to be an accept state. And now I want to start counting zeros. In order to do that, I probably want to start by having a transition into kind of like the 0 counter state, which is going to count, is just basically going to loop onto itself every time it sees a 0 and push on zeros onto the stack. And then the second when it sees a 1, it's going to move to Q3. And Q3 is going to start counting ones until it's done, at which point it's going to go to a final accepting state. Let's look at the transition. So this is something new, which I'm introducing a couple of new things. First of all, that you can have epsilon transitions. So this is an NFA. For Q1, I'm actually just going to have epsilon and then epsilon to $, because the stack is empty. Now, Q2, that's the 0 counting state. So it's going to transition back to itself on a 0. And then I'm not popping anything from the stack, so it's just going to be epsilon. And then I'm going to push a 0 onto the stack. Now, eventually you're going to stop seeing zeros and start seeing ones. So that will be my transition to Q3. And now I'm going to pop zeros off the stack, and I'm not going to replace them with anything. So it's 0 to epsilon. And then similarly, I'm going to have on Q3 a 1 and then 0 to epsilon. Great. So basically every time I see a 1, I'm going to start popping ones off. I'm going to start popping zeros off the stack. And then at the end, since I'm done counting ones, I'm going to take an epsilon transition, and assuming that the stack is empty, I'm not going to push or pop anything, but just basically checking to see that it's empty, and it's going to go into this final state. So remember that this symbol, this like structure that we have here, is the input symbol, comma, the thing that we pop off the stack to the thing that we push off the stack. In other words, like what we replace. Great. So I drew this pushdown automata and I have these transitions. Let's check it to make sure that it actually accepts strings like we expect it to. So I'm just going to write down a couple of examples and see if it works kind of the way I want it to. First of all, the empty string. Well, Q1 is accept, so that's good. And you don't have to read anything. So basically 0 to the 0, 1 to the 0 works. Now, let's say that I have something like 0, 1. Okay, so let's follow along. And first I'm going to take this epsilon transition because it doesn't matter. And now I'm going to read this 0, and I'm going to push a 0 onto the stack. And now I'm going to read a 1, and I'm going to pop that 0 off the stack. At this point, there's nothing left on the stack, so I can take this epsilon transition, and I can check that this stack is empty, so we are again good. Awesome. All right, let's look for a string that doesn't work. Let's say a string with 0 and then 2 1s. All right, so this should fail. All right, so let's follow along, and let's say that first we're going to take this epsilon transition because we always do, and now so let's say, actually let's do this in green so that it looks a little bit different, but let's follow along on this picture. Okay, take this epsilon transition, that's good, and now I'm going to read a 0, and so that's going to allow me to push a 0 onto the stack. Great. Now I'm going to read a 1, which is going to cause me to pop a 0 off the stack. So now my stack is empty. Okay, well, looking at this transition here, 0 to epsilon, I no longer have zeros to pop off the stack. So even I can't transition on this 1, so I fail. And probably for completeness, let's say we want to see an example where there are more zeros than 1s. So let's say 0, 0, and let's follow along. Epsilon transition always gets taken. 0 gets pushed onto the stack, 0 gets pushed onto the stack. And so I have a stack with 0, 0, but I can never go to Q3, and therefore I can never go to Q4. So I can see how 0, 1, 1 fails and 0, 0 fails. And just remember that if you end up in Q4, but there are more input letters to read, so if there's still like 1s and 0s on the input string, then this will be also a fail. So you can think of Q4, the string has to be empty by the time it gets there, or it will not accept. At the beginning of the video, I stated that A is a context-free language if and only if some pushdown automata recognizes A. And I showed you a pushdown automata for the language of an equal number of zeros followed by an equal number of ones. I haven't actually proved this theorem, and I'm not going to in this video, but I am going to remind us of the example that we did in the previous video, where we talked about the grammar of this language, which was 0 to the n and then a hashtag with 1 to the n. And so with a couple of changes here, right, if I remove this hashtag and then I say, look, B is just going to go to epsilon, the empty string, I have this language that looks like 0 to the n, 1 to the n for n greater than or equal to 0, which, since the variable doesn't matter, it is 0 to the k, 1 to the k greater than or equal to 0. So this highlights a couple of different things. Just, hey, this is a grammar with an equivalent language and an equivalent pushdown automata. It just looked a little bit different before. And this hopefully starts to convince you that A is a context-free language if and only if some pushdown automata recognizes A. Again, not a proof, just a simple little example. One thing I want to point out is that there are different ways to draw a pushdown automata and to write a context-free grammar. So let's take a look again at our language that we've had, which is 0 to the k, followed by 1 to the k for k greater than or equal to 0. Here's another way to write a context-free grammar that's different from what we had on the previous slide for it. We'll have phi be this start state s, sigma will be 0 and 1, and then I just have two rules, which is s goes to 0, s1, and s goes to epsilon. And so this is just a little bit shorter than what we had on the previous slide, but it's equivalent. So I'm going to leave you with an exercise which is to draw a different pushdown automata for this language D that we've been talking about. One that is equivalent and is still, so it still should be correct and sound. All right, that's all I have for you, so thanks for watching.